All right, welcome everybody to, it's now the fourth seminar in this year's, right? And the third seminar in this year's list. Francois Gelis at the Institut de Physique Théorique in Saclay has kindly agreed to give us two talks this time around, with a gap in between for external reasons. And he will talk about isotropization in heavy ion collisions. Just should say that Francois has a very long history in the realm of heavy ion collisions. I remember reading his habilitation thesis very often, where he was talking about translating color glass condensate initial conditions into something, into initial conditions for heavy ion collisions, with many other things that he has done. He's been doing postdocs in many places, including the United States. So he's well traveled and been essentially to all places where heavy ion theory is happening. So I'll just let him now go and introduce us to the topic of isotropization. Take it away.
Okay. Thank you very much for the introduction. And thanks a lot for this kind invitation to speak in your seminar. So I will be talking of a problem I've been thinking about for a long time now, which is isotropization and thermalization in heavy ion collisions. So this is the outline. In black is the topics I will cover today. In blue is what will be in the second talk. I will talk about or recall you how effective the hydrodynamical description is in describing the evolution of the matter produced in heavy ion collisions. Then I will have a part on more historical list of old ideas and concepts about thermalization. Then I will talk about how we think about the initial state of a heavy ion collision in terms of QCD and the color glass condensate, which plays an important role in this description. And the last topic I want to cover today is to discuss briefly some of the past attempts at studying the question of thermalization and isotropization. Mostly, I will discuss semi-classical approach and also kinetic theory. And then I will end with a very brief discussion of what are their shortcomings and why it's desirable to go or to describe this at a more fundamental level. So let me start with the introduction. So as you know, matter is made of atoms. Most of the mass by far is located in the atomic nuclei. And the atomic nuclei themselves, if you think about them at a more fundamental level, they are made of quarks and gluons, bound together by the strong nuclear force. So the strong interaction, the strong nuclear force, is described by a quantum field theory known as quantum chromodynamics. It's a quantum field theory that describes the quarks, the gluons, and their interactions. So the fields present in this theory are the quarks. There is one field for each flavor of quark. And the gluons. So the quarks and gluons carry a charge called the color. For the quarks, there are 3 different colors. For the gluons, there are 8 possible colors. And in the Lagrangian or in the Feynman rules, there is one interaction that connects a gluon. The gluon is represented by this spring-like line. So there is a vertex connecting a quark, an anti-quark, and a gluon. whose Feynman rule is proportional to a coupling constant called G, and then a certain, it has a certain dependence on the color A of the gluon and the colors I and J of the quark and antiquark. There is also a triple gluon interaction. I've not written it in full here because it has also a fairly complicated dependence on the momenta of the gluon, so I've written only the color part of it. It's also proportional to the same coupling constant, and it has a slightly different dependence on the colors. And there is also a 4-gluon interaction, for which I didn't write the color dependence because it's a bit more complicated. The matrices little ta and big ta that appear in these rules are special unitary matrices. They are in SU3 more specifically. And the little ta is in the fundamental representation of SU3, and the big ta is in the adjoint representation of SU3, which has dimension, which is made of matrices of dimension 8. The Lagrangian is really very much, at least on the surface, very similar to the Lagrangian of QED. It has a term which you can write in a compact way, like -1/4 of f squared, where f is a field strength, plus a Dirac term, which is in psi bar times a covariant derivative minus the mass times psi, with a sum over all the flavors. And this Lagrangian has only a few dimensionful parameters. It has the masses of the quarks that appear explicitly in the Lagrangian, and it has the coupling constant, which is hidden in the covariant derivatives and the field strengths, or equivalently, it's often traded for what is called the QCD scale, this parameter lambda QCD, and it's a scale at which the strong interaction becomes becomes large due to the running coupling effects. Speaking of which, so we define alpha s as g squared over 4 pi. It's just a convention. It's a number that encodes how strong is a strong interaction, and as like in most quantum field theories, this coupling constant depends on the energy scale. And what I've written below is a formula that tells you what is the running of this coupling with energy E at one loop, so in an approximation that takes into account corrections of order g squared. And you see that this formula depends on the number of colors and flavors, but if you have 3 colors, so NC equals 3, and with the number of flavors we know, which is we know in nature, which is 6, this number 11 NC minus 2 NF is positive, and therefore the coupling constant decreases when you increase the energy scale. It doesn't increase very fast because it's only logarithmically, or like the inverse of the logarithm of the energy, but it does decrease. And this is seen experimentally. So the plot below shows a compilation of many kinds of experimental measurements from which, so cross sections typically, from which you can extract the value of alpha s at a certain energy. And then the points are represented as a function of the energy, which in the plot is called Q. And what is shown in black, I guess, is the theoretical curve, probably including 2 and 3 loop corrections. And you see there is a quite good agreement between the theoretical prediction and the experimental measurement of this coupling constant over energy scales that span several orders of magnitude, see from 5 GeV to 2 TeV. So this is an important fact about QCD. It's called asymptotic freedom. And it's what makes QCD a practical theory for making predictions in scatterings at high energy, because at high energy the coupling constant gets fairly small and sufficiently small for perturbation theory to have rather good predictive power. Another feature of QCD, which is a little bit the counterpart of asymptotic freedom, is color confinement. So what is shown in this graph is, this is not experimental data, it's calculation done on a computer using lattice QCD, and it's the binding potential between a quark and an antiquark, heavy quarks, so that they don't have any kinetic energy, they are static. So it's a potential energy as a function of distance. And you see that at short distance, what did I do? At short distance, I have to, okay, I'm sorry. At short distance, you have 1/r shape in this potential. So it's a bit like a Coulomb potential in electrostatics. But then at long distance, if you recall electrodynamics, in electrodynamics, the potential will go to 0 at long distance, while in QCD, this potential rises linearly with the distance. And what this implies is that the force, which is a derivative of the potential, the force between the two quarks, is a derivative with respect to the distance of the potential, so it goes to a constant. So this prediction of QCD is that the force binding two quarks is not decreasing at large distance, but it goes to a constant. And of course, this cannot truly happen because or at least if something else has to happen, because if the situation was like this without anything else, it means that a quark located in an atom on my desk will feel the forces of the or produced by all the other quarks in the universe, no matter the distance. Okay, so what happens is that the quarks combine themselves or arrange themselves into bound states, which are made of either a quark and an antiquark or three quarks. So bound states which are color neutral. So for instance, with three quarks, you can indeed make states which are singlet under the strong interaction. And then these bound states being singlet, the residual force at long distance between two such bound states is much weaker than the force we saw in the previous slide. It's a little bit like the van der Waals force in between two electrically neutral molecules in electrodynamics. But here, in fact, the force will decrease even faster because the lightest bound state in QCD has a mass, unlike the photon. So what is shown here is a table of the masses of the lightest hadrons. So you see there is a pion, kaon, rho, k star, the nucleon, the lambda, and so on. And it's not, well, it contains both experimental measurements. These are the gray rectangles. So it's an experimental measurement of the mass of this particle with the associated experimental uncertainty. And then the red points are the result of a calculation in lattice QCD. So one can calculate the masses of hadrons in lattice QCD. And this is a result of the calculation. And the points which are shown in blue were the particles that were used as input data to calibrate the parameters of the lattice calculation. So they have no error. by design, in fact, because they were used as input for the calculation. So this is a calculation that had, I guess, only the U and D quarks. Oh no, sorry, U and D quarks, but that are degenerate, a strange quark with a mass which is different from that of the U and the D, and the lambda QCD parameter. So in total, there were 3 dimensionful parameters to set. That was done with the mass of the pion, kaon, and sigma. So you see that QCD, despite the fact that it's complicated at a large distance because of confinement, predicts quite accurately the masses of the hadrons. This is another result from lattice QCD that shows the more thermodynamical quantity. It's what is considered here is a gas of quarks and gluons or hadrons, depending on the temperature scale, and what is shown is the pressure of this gas, so that's a vertical axis, as a function of the temperature. And you see that if you look at these curves, for instance, the pressure starts from very small value and then rises sharply around 200 MeV and then reaches a plateau at higher temperatures. I should say that what is shown is the pressure divided by the force power of the temperature, because the pressure has dimension of an energy to the 4, and you have to scale it out by the temperature to the 4 so that you're not looking at the trivial rise due to the increase of temperature. So what happens around this temperature scale is believed to be a phase transition, or like a phase transition, where the bound states made of quarks melt into a gas of unbound quarks and gluons. And what happens is that simply you're increasing the entropy of the system, because the number of degrees of freedom per unit volume is suddenly increasing dramatically. And the range curve is the same computation, but with only gluons and no quarks, but it shows also the same feature, at least qualitatively. So this phase transition is the lattice calculation that gave these curves is done along this axis, where you rise the temperature at 0 baryon density. It's the only place of this diagram where these calculations are doable easily. And then the rest of this phase diagram is a kind of guesswork. So what is believed is that there is a certain curve in the plane of temperature and baryon density, below which you have confined quarks, so a hadronic phase, and the atomic nuclei that we know are located somewhere here at slightly non-zero baryon density and low zero temperature. And then if you go out there at high temperature and high baryon density, you have deconfined quark matter, which is called the quark-gluon plasma. What else? Yes, there is another phase which is located at high density and very low temperature, which is believed to be superconducting from the point of view of the color interactions. So it's called a color superconductor. But it's only it can only be studied theoretically at a high baryon density. So at intermediate densities around here, we don't really know what's going on from the theory perspective. And somewhere here, I've drawn an elongated blob because we still don't know exactly where it is, are the neutron stars. The matter inside the neutron star is obviously denser than the normal nuclear density, so it has to be on the right of normal nuclei. But we don't quite know experimentally if the core of neutron stars is made of ordinary nuclei or nucleons, or if it's made of a more exotic phase like quark superconductor. This transition has occurred once in the history of the early universe, because as you know, the early universe was very hot at the beginning, shortly after the Big Bang, and then as it expanded, it cooled down, and at a time of about 1 microsecond, it went through this transition here, and then nowadays, of course, the matter in the universe is made of hadrons. What is important to realize is that this phase transition in the early universe didn't leave any imprint that we could see nowadays using astronomy. So if we want to study this transition experimentally, we have to try to recreate these conditions in the laboratory. So this is what I was saying before. So you see the confinement transition is at a few microseconds after the Big Bang. It's located here. But what we can see using astronomy is much later. It happens much later. So you see nucleosynthesis is 3 minutes after the Big Bang. And then the first light we see from the early universe is like 200,000 years after the Big Bang. So it's not what we see in astronomy is very far from this phase transition. So the idea behind heavy ion collisions is to try to recreate in the laboratory the conditions of high temperature to produce a quark-gluon plasma. So the strategy is to take large nuclei, like, I don't know, gold nuclei or lead nuclei at the LHC, and to collide them at very high energies. And then, in a short volume and for a very brief duration, there will be a very high energy density or temperature at the location of the impact between the two nuclei. And then if this really happens, locally there will be the formation of a droplet of quark-gluon plasma. It will expand in the vacuum around it, and then it will of course rehadronize later on. So this is this arrow going down. And what is done is to measure all sorts of things in these collisions to try to pinpoint signatures of the quark-gluon plasma. So now I come to the hydrodynamical description. So theorists like to divide the evolution after a collision in several stages. So this is a z-axis, it's the axis of the collision, where the direction of the momenta of the two nuclei. This is time, and then you have these sheets corresponding to fixed values of the proper time. At the very beginning, you have strong color fields. Then you have quarks and gluons out of equilibrium, and then perhaps they get closer to equilibrium. At some point, you reach the temperature of the phase transition, and then they turn into hadrons, whose evolution can be described either by hydrodynamics or kinetic theory. And then you have a surface called the freeze-out surface. This is a surface where the mean energy per particle is below the thresholds for interesting reactions. So after this, beyond this surface, essentially the hadrons you have do not interact anymore, and the properties of the system are frozen. And the main aspect of this is that a good deal of this evolution is well described as a fluid expanding into vacuum according to relativistic hydrodynamics. So I will show here a few experimental plots. So the data points are actual measurements at the LHC or at RIC at Brookhaven, and the curves are theoretical calculations using viscous hydrodynamics. And you have the value of the viscosity here. It's the important aspect to take home is that the viscosity necessary to have a good description is very small, extremely small. The ratio eta over S is the shear viscosity divided by the entropy density. It's dimensionless, so it's a number you can compare across various substances. And in fact, the eta over S around 0.1, 0.2, which is found here, is smaller than that of liquid helium that we know is a superfluid. So you see, this is one example of data which is super well described by hydrodynamics. This is another kind of data. So I will not explain what this data is. The message I want to carry across by showing these plots is that there are many quantities that are very well described by hydrodynamics in heavy ion collisions. So this is another one, yet another one. So you see, and there are many more, of course. And in all those descriptions, small viscosity is necessary. So the natural question is, why does it work so well? So if you look into the equations of hydrodynamics, so the relativistic Navier-Stokes equations, you expect, and you think about how they are derived, you expect that it might work when the pressure anisotropy, so the difference between the pressure along the beam axis and the pressures in the transverse directions is not too large. The system should not be too far from thermal equilibrium, otherwise there will be a lot of dissipation when the system equilibrates. And it must have a very low viscosity, otherwise this agreement will not work so well. And any of this is easy to get from first principles if you think of describing the system from scratch. So now I want to discuss a few old ideas about thermalization. Let me start with the second law of thermodynamics. So as you know, thermodynamics is kind of one of the big successes of physics in the 19th century. And it has several laws. The first law of thermodynamics is easy to understand from the underlying mechanics, because it's just stating that if you do your accounting correctly, energy should be conserved. It's just energy conservation. But you have to take into account the energy that goes into the microscopic motion of the atoms. But the second law about the increase of entropy for a closed system has remained rather mysterious. By mysterious, I mean when you start asking where does it come from at a microscopic level. So if you start from the equations of the mechanical motion of the atoms in a system, and you ask, can I see the second law of thermodynamics from there? Then it's rather non-trivial, and I will explain why in a second. But the main problem is that the microscopic laws of dynamics are usually time reversible, and they do not impose a preferred direction for the flow of time. While when you state that the entropy increases with time, there is clearly a preferred direction for the evolution. So there are various concepts of equilibrium. One is called kinetic equilibrium. So it means that if you look at a single particle in a closed system, but the system contains many particles, and you do the statistical sampling of the number of particles that have a certain momenta, you will find a distribution, which in classical physics will be a Boltzmann distribution, and this is called kinetic equilibrium. Another concept of equilibrium is so-called microcanonical equilibrium. So it's idea that if you have a macroscopic system with energy, all the microscopic realizations that produce a system with this total energy are equiprobable, assuming you have no other knowledge about the system. Another concept that was introduced in the discussion of equilibrium is that of ergodicity. So the idea is that if you follow one particle for a very long time, and you do you compute, for instance, the distribution of the momentum it has at various times, you will find the same result as if you do a snapshot in time and you do this average over all the particles of the system at this precise time. So in a sense, the idea behind ergodicity is that the trajectories of individual particles are sufficiently complicated to explore the entire available phase space to them. So let me start by some reminders about the Boltzmann equation. So the Boltzmann equation is a kind of approximation of the dynamics of the system, where you summarize the description of the system by what's the momentum distribution of the particle. So this function f of p, which depends also on time and position. And the Boltzmann equation is telling you how this distribution evolves in time and space according or due to the collisions among the particles. So it has this operator. This is an operator that looks at the rate of change of f as you move in space and time. And the right-hand side is called the collision term or the collision integral. Here it's written for a non-relativistic, not non-relativistic, but in classical mechanics, sorry. So you have two terms, a term with a plus sign and a term with a minus sign, because you have collisions that will produce a particle of momentum p, this contribute with a plus sign, and collisions where a particle of momentum p gets scattered and changes momentum. So this goes with a minus sign in the equation. And the rest here is the first line is just the phase space in integration over the phase space of all the other partners of the collision. So the particles of momenta k, k prime, p prime with momentum, energy and momentum conservation. And the dynamics, the microscopic dynamics is totally encapsulated in this m square. It's like the transition probability for this scattering to happen, and the fact that you have the same m square for the term with a plus sign and the term with a minus sign is a translation in the Boltzmann equation of what I said before, that the microscopic dynamics is reversible. So you have the same probability for this reaction happening in one direction or in the reverse direction. And now, as you probably know, a consequence of the Boltzmann equation is the so-called H theorem that was proven by Boltzmann. So you can define an entropy density, so it's density in space of the entropy, and then an entropy flux, it's this vector J. which is defined with the same density times the velocity of the particles. And the H theorem is that the drift of the entropy, so the time derivative of the density plus the divergence of the flux, is equal to a source term, sigma, and sigma is positive definite. So sigma is cannot be negative. And furthermore, you can prove easily that sigma is zero only when the distribution is a Boltzmann distribution, so exponential minus beta times the energy. And this is proved only from the conservation law, so from the fact that this equation conserves the number of particles and conserves the total energy in the system. So with these two conservation laws, you arrive at the fact that the equilibrium, so when the entropy is maximal in the system, is when the distribution of particles is exponential of minus beta times the energy. Beta is the inverse of the temperature. And you have generalizations of this result when you include quantum statistics, but except you don't get a Boltzmann distribution, but you get a Bose-Einstein distribution for bosons and a Fermi-Dirac distribution for fermions. So now, shortly after, at this stage, Boltzmann was satisfied because he thought he had proven the second law of thermodynamics from first principles, because he had exhibited this quantity sigma, which is the rate of increase of the entropy, and it's positive. But then an objection was raised by Poincaré a few years later, and now it's known as the Poincaré recurrence theorem. So it's based on Liouville's theorem, which is that the volume occupied in phase space by a system is constant. The volume in phase space is conserved by the dynamical evolution if you don't have if you have only conservative interactions. Another consequence is that phase space trajectories cannot intersect. And the Poincaré theorem says that any dynamical system whose conserved energy manifold has a finite volume has to return arbitrarily close to its initial condition. And the proof is really easy. So what is shown here by this disk is the finite volume in phase space accessible to the system. Of course, for a genuine system, the phase space has a huge dimension. It's not two-dimensional like in my picture. And then I take a little volume in phase space and I move it around by preserving its volume. So by preserving the area of this tube. And then, eventually it will it cannot intersect with itself, except by going back to the starting point. And because the volume accessible to it is finite, it will have to return to its starting point eventually. Of course, so this looks like a serious objection to Boltzmann's result, but this recurrence time, so the first time, the smallest time necessary for the system to return close to its initial condition increases extremely rapidly with the number of particles in the system. So for a system which is macroscopic and that has lots of atoms in it, for instance, this recursion time is huge. So it's an obstruction in principle, but it's not really an obstruction in practice. What I want to discuss now are more recent ideas about chaos, because it's another angle to think about this problem. So if you consider a generic system that has n degrees of freedom, so it means its phase space has two n dimensions, so because you have the n coordinates and n momenta. And if you fix the energy, that's one constraint, so the accessible phase space is now 2n-1 dimensional. And one question you can ask is, does a typical trajectory of this system explore most of this allowed domain or not? So let me start by systems that do not do that. So these are so-called integrable systems. So an integrable system is a system where you have as many conservation laws as you have degrees of freedom. So you can view them as a product of n one-dimensional systems if you want. As you know, a one-dimensional system in mechanics is always integrable because you have energy conservation. And so an integrable system is like a collection of non-interacting one-dimensional systems. And in this case, the accessible phase space is an n-dimensional torus. So when you fix these n conserved quantities, you further restrict the accessible manifold, the manifold accessible to the system, and it becomes n-dimensional, and it has the topology of a torus. This is not very important. So what you can say is that the manifold of constant energy can be further subdivided into manifolds corresponding to all other conserved quantities being fixed. And you see that a system, if once you fix these conserved quantities, a system will stay on this torus and will definitely not explore the totality of the constant energy manifold. So it will be very far, in fact, as far as you can imagine, from systems that will reach microcanonical equilibrium. And then the big question in the 50s and the 60s was, what happens if you consider a chaotic system? So a chaotic system is a kind of the contrary of an integrable system. The only conserved quantity is the energy and nothing else. And now if you have a chaotic system, you could still ask whether the trajectory in phase space will explore the full constant energy manifold. And for a long time it was believed that the answer was yes, until this result by Kolmogorov, Arnold and Moser in the 50s and 60s, which essentially says, answer negatively to this question. They say that even when you turn interactions that will lead to chaoticity in the system, many of those invariant tori will survive, and then you will have some domains where you truly have chaotic dynamic, but not all dynamics will be chaotic. And here I've done a little computation with a very simple system, which has this transition from order to chaos, or partial chaos. So it's a system with 2 degrees of freedom, x and y. So the phase space is 4-dimensional if you include the velocities. And then if you suppose for a moment that you set k equal to 0, so you don't have this last term, then this Hamiltonian is separable as a product of 2 subsystems which are one-dimensional. It separates into the variables x plus y or x minus y. So at k equals 0, it's integrable and the dynamics is totally regular. But then it becomes chaotic when you increase k. So what I try to plot is what happens in phase space, but with a restriction, because phase space is 4-dimensional and I cannot really represent anything in 4 dimensions. So I've taken slices through the phase space. I'm taking the slice which sits at x dot equal to 0. So I'm making a 3-dimensional slice in phase space, and I mark a point, a colored point, every time the trajectory intersects this x dot equals 0 plane. And the different colors correspond to me having chosen different initial conditions. So what you see at the start is what you have at k equals 0. So these intersections are regular. They really look like what you will have if you intersect a torus by a plane. But now let me turn on the interactions. So you see k increasing here, and you see, let me pause on here, you see that now these regular curves of some of them are still here, like here, but if you look in this region, you see scattered points of all colors. So it means that the curves corresponding to different initial conditions, they explore the same regions. Now if you focus on one color, for instance, some shade of green, you see that these points are scattered over a large fraction of this surface, not just on one curve. So this is a signal of chaos, but you see it's a mixture of chaos and still regular motion for some initial conditions. And then as you keep increasing k, the system will become integrable again, or almost integrable again. So this is at large k. So, and it's going back to small k. So this is one example showing that chaos is not always producing a sufficient mixing to fill all the available phase space. So now, so now I want to turn to quantum mechanics, because in quantum mechanics, the concept of thermalization is even more, how to say, problematic or surprising, I would say. So first of all, I want to introduce a little known formulation of quantum mechanics, which is equivalent to the one you know, but is a bit more appropriate for discussing these things. So on the left of this table, you have the usual description where you have a density operator that describes a possibly mixed state for a quantum system. It evolves according to the von Neumann equation, like this. And on the right, you have the same description, but in terms of what is known as a Wigner distribution. So a Wigner distribution is a function of coordinates and momenta, classical coordinates and classical momenta, and there is a one-to-one correspondence between the density operator and the Wigner distribution. And the analog of the von Neumann equation is the so-called Moyal equation or Moyal-Grunewald equation, which tells you that the time derivative of W plus a certain bracket of W with the Hamiltonian is equal to 0. And note that here you have the classical Hamiltonian, while here you have the Hamiltonian operator. And I will not write explicitly the form of this bracket. It's known for simple systems. But what I want to stress is that this bracket contains h bar. So you should view it as a certain h bar dependent deformation of the usual Poisson bracket. So in fact, if you expand it in powers of h bar, it starts by the Poisson bracket, and then it has a first correction. It's an infinite series, and the first correction is of order h bar squared. So this formulation of quantum mechanics makes it quite transparent in which sense quantum mechanics goes into classical mechanics, because in this formulation, it's just as this bracket goes to the ordinary Poisson bracket, and then you recover the Liouville equation for the density in phase space. So now let's go on with the question of chaos and thermalization in a quantum system. So the problem is that Schrödinger's equation is linear. And its spectrum, if the Hamiltonian is Hermitian, its spectrum is real valued. So the evolution of a wave function doesn't contain anything that blows up in time, because all these phases have modulus equal to 1. Okay, so there is no instability at all. There is no Lyapunov exponent, at least clearly visible in the evolution of the wave function, unlike classical chaos. So one legitimate question is, suppose you start from a classical system that you know has chaotic behavior, and you quantize it, then what happens? How do you see any features of the quantum system that are due to the fact that the underlying classical system was chaotic? And the answer is probably, but it's a rather indirect feature. The conjecture goes back to the late 70s by Michael Berry. And the conjecture says that the complexity of the classical dynamics translates into the complexity of the eigenfunctions for the states of high energy, the eigenstates of high energy. And in a more concrete way, what the conjecture says is that you can treat these wave functions or these eigenfunctions as if they were random functions drawn from a Gaussian ensemble of random functions with a two-point correlation function, which is essentially the Wigner transform of the delta function that says the energy is constant. So you take the classical Hamiltonian, you put a delta function saying that it has to be equal to a certain energy, and you Fourier transform on the momentum to get this variable S, and that's your two-point correlation function of this Gaussian ensemble. And if you take it in reverse and you compute the Wigner function associated to one of those eigenfunctions, you just use this result and you will find a delta of E minus H. So in a sense, the Wigner distribution of such a quantum system is precisely the microcanonical distribution in phase space. So this will be like the absolute counterpart of an integrable system, because there you will have something that looks like a microcanonical equilibrium just by looking at a single eigenstate of the system. If you look in the literature, this goes by the name of eigenstate thermalization sometimes for this reason. So now I want to discuss briefly, I'm going back to the problem of heavy ion collisions, and I want to say a few words about the initial state. So the nuclei you're colliding contain many quarks and gluons, so the main difficulty is how to deal with collisions involving a large number of these particles. If the two projectiles were dilute, you will do the same perturbation theory as usual. You will take one parton in each of the two nuclei and compute a cross-section with them. The problem is that in the dense regime, you could have many such processes going on at the same time. You could have more than one quark or gluon participating from a single nucleus. So this is getting more complicated. And what we use is we don't start from the directly from the Lagrangian of QCD, but we use some approximate effective description in which you say that the fast partons in a nucleus have their dynamics frozen by time dilation. So if you sit in the rest frame, in the center of mass frame of the collision, you see these partons moving almost at the speed of light in either direction, and therefore to you they appear as if they were not evolving in time because of Lorentz time dilation. So they are described as just flux of color charge. This vector J mu, it points along the light cone direction minus. This is for left moving charges. It depends on where you look in the transverse plane. And the x plus dependence is totally Lorentz contracted. So x plus is restricted to be at most 1 over this cutoff lambda. What you don't know is what is the precise distribution of this color charges, so this function rho, especially in a given collision. So because that depends on what was the precise configuration of the quarks inside the nuclei precisely at the time of the collision. So the best you can hope is to describe that in a statistical way by a probability distribution, which is denoted W of rho. And in this description, the partons that have longitudinal momentum less than this cutoff, they are described as the usual gauge fields. And there is a coupling between the two, so the fields are coupled to the currents in this way. So this effective theory goes like this. You have the Lagrangian describing the gluons and their interactions, and then the piece that couples these gluon fields to the color sources. J1 and J2 are the sources for the two nuclei, respectively. And for instance, if you ask what is a stress energy tensor, it has a well-defined expansion in powers of the coupling constant. It starts by 1 over g squared because these currents are of order 1 over g. But otherwise, each time you add a loop to the description, you get 1 more power of g squared. At the leading order is C0, and then you have no loop at all. It's all classical fields. And in fact, the components of T mu nu are given by the same formulas as in quantum electrodynamics in terms of the chromoelectric and chromomagnetic fields. So they are given here. And another feature of what happens at the very beginning is that the fields E and B are longitudinal, so they are aligned with the collision axis. And if you work it out, this implies that first of all, there is no energy flux. The pointing vector is 0. The transverse pressure is equal to the energy density, to T00, and the longitudinal pressure is negative and equal to minus the transverse one. So it's very far from being isotropic. Isotropy will mean equal transverse and longitudinal pressures. And if you follow that through time, you see, so what is shown here is transverse pressure divided by the energy density in green, longitudinal pressure divided by the energy density in red. And they get a bit closer to one another, but they never isotropize. You see that the longitudinal pressure goes to 0, while the transverse one goes to 1/2 of the energy density. It's not isotropic by far, and it will never become isotropic at 3 level. So now, how can we go further and include loop corrections? So this is a rather general result that we've proven 10 years ago, roughly. It says that you can relate any inclusive observable at one loop to its value at leading order, so at 3 level, by applying this operator. And in this operator, there are two things. The gamma mu nu is a certain function of two coordinates u and v, which can be calculated analytically in certain cases. And Tu and Tv are operators. You should think of these operators as derivatives with respect to the initial condition of the color field. It's a bit more complicated in practice because the initial condition needs also the time derivatives of the fields, but in spirit it's like that. It's a translation operator for the initial condition of the field, and the formula below is actually exact. So if you exponentiate this operator weighted by some function alpha of u, and you act with something that depends on the initial condition of the color field, you get the same quantity with a shifted initial condition for the field. This is really the definition of this operator. And if you work out what is the effect of having one loop corrections on the pressure, the trend is that it will increase the longitudinal pressure, but it also, the one loop corrections also suffer from instabilities that limit their applicability in practice. So maybe, Heribert, should I stop here because I see that I've reached my time, and perhaps it's better if I start from here next time.
That's perfectly fine with me. If you feel comfortable stopping here.
No, it's just a few slides, but this to explain them carefully, this will take at least 5 to 10 minutes. So
I'm happy with another 5 to 10. If you'd rather do it now, I'm happy with it. If you want to do it next time, your choice.
No, actually, it makes sense if I do it next time. It's a more natural break.
Okay.
So maybe let me to end the talk of today. Let me advertise what I will discuss next time. So first of all, I will discuss how the problem of isotropization in heavy ion collisions has been approached in the past, so by either kinetic theory or semi-classical approximations. And I will show you that each of these two approaches has some caveats that make it desirable to have a more fundamental approach. And then the bulk of next parts will be one approach which is based on the so-called 2pi effective action, which in a sense overcomes the problematic aspects of both the semi-classical approximation and kinetic theory. And I will present you some numerical results obtained in this framework.
Well, then let's thank you for a very clear and very broad introduction to the topic. It should have become clear to everybody listening to you that you're drawing together from many sources, because this is in principle, right? It's a topic that builds on insights from both classical mechanics and quantum mechanics at the same time. So it's clearly not trivial. I hope you are all at least partially familiar with the backgrounds there. I mean, you probably would feel more confident if you had a little more grounding in this, but you have a starting point now, right? For next week, you can read up a little bit more. You have a very good start, I think, from what Francois gave us today. But do you have any questions that fit in at the moment? And anybody online, please just speak up. Should be easy enough. Yeah, one. Go and shout. This is Daniel.
It might be a very basic question. I don't know much about chaos theory. So when you talk about quantizing a classical system that had chaos, or had chaotic behavior, why do you expect the quantum system to have chaotic behavior? When I think of, it seemed as if, you know, there was a conservation of chaos, that because the classical system had chaotic behavior, the quantized system should have some form of that. Is that always true? Or? Yeah,
this is a fair question. So I guess the concern people had was that there is in principle a formal limit you can take to go from quantum mechanics to classical mechanics. You just take h bar and you decrease it until it reaches 0. So it's not like quantum mechanics is a totally disconnected theory from the underlying classical system. So in a certain limit, if you solve Schrodinger's equation with a free parameter you call h bar, and you take h bar to 0, you ought to be able to reproduce the classical mechanics, which is chaotic for this particular system. So the interrogation or the paradox people had was that when you stare at the solutions for the wave equation in quantum mechanics, the time dependence of it, so which is here, doesn't look chaotic at all, because the time dependence of this exponential is perfectly smooth as long as the energies are real valued, and no matter how small is h bar. So the interrogation was, what happens to this to this quantum system when the underlying quantum system is a classical system is chaotic, and when h bar is small. So somehow the feeling is that the quantum description should know a bit about the fact that the underlying classical system is chaotic because you take a small h bar. And so the big question was where is the chaos in the quantum description? And then this was, I would say, partly answered by Berry's conjecture, which, the status of this, as far as I know, is that it's not a rigorous mathematical result, but it's based on a lot of numerical evidence. So where various people studied things in numerical simulations, and they looked at these properties. There is a very well-known paper by Mark Srednicki circa 2005-2006, where he did some numerical experiments to explore these ideas. And what he shows, for instance, is that by taking a quantum system or the eigenstate of a quantum system, and by measuring sufficiently inclusive quantities, so for instance the distribution of momenta for one particle in this, using the wave function of this quantum system, he found something that looked like a Bose-Einstein distribution for a single quantum state, which will be consistent with Berry's conjecture. So of course, when you take h bar to be larger, as you said, there is probably no reason to expect anything in particular. The quantum mechanics is probably quite different from the underlying classical mechanics.
Okay, thank you.
I mean, the semi-classical limit is always a really tricky game, right? You will only you have to phrase your question very, very carefully. What can you expect to have a classical counterpart? Right? If you start from an extremely quantum initial state, right, it will have likely very little connection with the classical system, right, directly. And since you usually phrase these questions from different ends, oh God.
Yes, yeah. In a sense, yes, but there is one aspect where I would perhaps milden a bit what you said. It's if you use this description of quantum mechanics with Wigner distribution in phase space, yes, then this Wigner distribution should go back to the classical phase space density with the same evolution equation, because this equation goes to the Liouville equation. And we know that for a chaotic classical system, for a classical chaotic system, the phase space density will kind of become uniformly spread over all the surface of constant energy. So it will be nice to see that arising from quantum mechanics as well when h bar is small. Because this object is exactly the same object that you have in both descriptions, this density in phase space. Has Heribert disappeared? Can you hear me?
I'm not sure what happened to Haribus. But
Yeah, he has disappeared.
Yeah.
Oh, he's back.
Hello, can you hear me?
Yes, I can
Okay.
hear you.
Yeah, we had a little hiccup. My laptop has overheated apparently.
Oh, okay. Yeah, so what I was saying just before you disappeared is that if you use this phase space description of quantum mechanics, you expect a rather smooth transition between quantum and classical mechanics. And since for a chaotic system, the phase space density will cover uniformly, or at least will cover big chunks of the constant energy surface, you would like the same to happen in the quantum mechanics at small h bar,
Absolutely.
which was a big non-trivial thing back in the 70s.
All right. Do we have any other questions? Now I don't see the audience because I'm in my office. So you guys just speak up if you have questions. I don't hear anything. Well, then let's thank you again.
Thank you.
We are looking very much looking forward to your second talk in 2 weeks' time. This time we will have something interspersed next week on a different topic. Daniel?
Yeah, the internet seemingly died here as well. I don't know what happened.
Okay. Well, then let's stop the recording and let's thank Francois again. Give him a hand, please. And then I'll stop recording.
I'm going to assume that